Go ahead and do this particular question though. We have a weight on the end of a string, and the weight itself is, I think the problem says that it's 10 grams or something like that. Um, I think we have found in a lot of these questions that the actual mass doesn't matter so much. But I don't know if the mass will matter here or not. The string is 20 centimeters long, and the system is, the word we would use here to describe it is oscillating, but it's doing so by going in a circular path, and that circular path is perfectly horizontal if I was holding it correctly. So does that kind of look like what we were talking about? All right, so this angle was 25 degrees, and this length was 20 centimeters, and the mass was 10 grams, although I was using a 200-gram mass. We want to figure out how long it takes to go around in a circle. Now, this problem asks about time. It might be hard to see the force problem in here, but is this an object that was clearly traveling in a circular path? And was it also clear that the object was traveling with what appeared to be a constant speed? So does that sound like uniform circular motion to you? So I think this is probably a uniform circular motion problem. So I think somewhere in here, we're probably going to see a centripetal acceleration, which will be equal to velocity squared over the radius. I think that's going to show up here. But this is in the force unit, so probably forces is where we're going to go. We know that using forces can tell us the size of an individual force or the size of the acceleration. Now, size of acceleration gives us this, but the problem didn't ask for any of these things, did it? What did it ask for? Time. So I think you're going to have to bring something to the table here, and I thought this was something that you guys would know. But it's clear that there's a lot of things I expect you to know that you don't. So I'm going to help you with this one. Distance equals velocity times time. Does this sound like something you've heard of before? I sure hope so, because we've used it in here. In this case, we want the time it takes to go around in a circle. That's called the period, by the way. And the distance that we're talking about here is a circumference. So if I want the time it takes to go around in a circle, I could just solve this for t. You'll notice I changed from a lowercase t to a capital T, because in this case we're talking about the period of oscillation. That word, period of oscillation, is going to come up this year. The oscillating is anything that has a repeated path or repeated pattern. Would you agree that the thing going in a circle is a repeated path or a repeated pattern? So period is a good way to describe that. A period is a length of time for something that repeats. So we use the word period in that context. So the period of a minute hand is going to be 60 minutes. It takes 60 minutes to go around the clock, stuff like that. Anything that has a repeated pattern of motion, we describe the time it takes using the word period, and that's almost always the capital T. So I think if I can figure out how fast it's going, I can figure out how long it takes. That make sense? Now, I like to do this problem symbolically, but I know that this one's going to have a lot of numbers in it, and you guys might like to do this problem numerically because it's easier. So I will give you the choice. Do you want to put the numbers in smaller steps, or do you want to do the whole thing symbolically? Your choice. All right, we'll do the whole thing symbolically. We did it with numbers in smaller steps in first period. So if you want to see that version, I'll post it. And in this class, we'll do the whole thing as a symbolic problem. Okay? All righty. I think we should start the same place that we start all force problems by asking ourselves, is this a first law problem or a second law problem? Second law problem. Has to be traveling in circular motion. Forces have to be unbalanced. So again, a lot of times these choices are made for you. You just have to understand the rules. So in this case, it has to be an unbalanced force because it's accelerating. It's accelerating because it's traveling in a circle. And there's things about that acceleration that are well known. First, it is well known that this object is traveling not just in a circle, but that it's going to be traveling in a circle at a constant speed the whole time. So we know that there has to be a net force towards the center of that circle. I am noticing that I'm very likely going to have to use the radius of that circle too. Are you noticing that as well? Maybe we should handle that right now. So I think when we say radius, we're talking about that distance, the radius of that circle. But I noticed that it can be defined by a triangle. Can you see the triangle that defines it? To keep this in terms of a symbolic problem, I'm going to use L for the length and theta for the angle. Is that okay with you guys? And I'll use M for the mass. Now it's a symbolic problem. We'll just drop in our numbers at the end. So can we all agree that the radius is going to equal L sine theta? Or do I need to do more math than that? We're all good there then? Alrighty. Let's start the next step, which is figuring out a free body diagram to describe this object. Can you tell me one of the forces that's acting on the mass while it's in circular motion? Gravity. I was grading somebody's pop quiz they did as a retake, and they put a capital G here. Is that okay? No, that is a forbidden letter. It is reserved for the universal gravitational constant, which we'll learn about next week, so you can't use it there. Acceptable are weight, mg, you could say force of gravity. All of those are acceptable, but you can't use capital G. My watch just told me to stand up. Okay, I promise. I'll stand up. Is there any contact force acting on the mass? I'm pretty sure it was connected to a string. So I'm thinking tension should probably be in there, yeah. And that's going to have to be something like that. Does that work for you guys? Is there anything else in contact with the mass? Any surface, wall, floor, ceiling? All right, so no normal force. No normal force means no frictional force. Any air resistance? We were told to neglect it, so we're going to neglect it. This appears to be the only forces acting in our system. But it looks unbalanced to me, so I think we're okay. Next step is to put a coordinate system that we can use to solve this problem. I think we need to use our rules for the coordinate system, which says that we should line up the coordinate system with the direction of the acceleration. And the acceleration is towards the center of the circle. So I'm going to use a coordinate system that is lined up with the horizontal and make this the positive x direction. Because that's got to be the direction of the acceleration, towards the center of the circle. That okay? That means y is going to be in that direction. All right, so I have one force that's off axis, right? So I have to break that up into its components. But I have to ask you guys before we do that, is this theta or is this theta? Are we talking about 1 or 2? Are we sure? Yeah, it's 2. Alternate interior angles is how I know it's 2, because I remember geometry. And I'm sure you guys do too, because you did so good in geometry honors and you wouldn't possibly forget anything you learned back then. So these are alternate interior angles. So angle number 2 is where theta goes. That means I'm going to take this and break it up into 2 components, a component along the y and a component along the x. Is that good for you guys? The opposite side is going to take the sine and the adjacent side is going to take the cosine. So this will be t sine theta and this will be t cosine theta. All good still? All right, well, seems to me like we've broken our forces up into their components. Means it's time to go to our next step, which is net force in the x direction equals MAC, and net force in the y direction equals 0. I still have people who will write MA for both of these. I still have people who will write MA for one and 0 for the other, but still put a 0 in here when they start doing their work. Pay attention. Pay attention. If you made this decision, stick with it. But MA is only going to go with one of these. There's only one force in the x direction, that is t sine theta, and that equals MAC. There are 2 forces in the y direction, that'll be t cosine theta equals mg. I'm just going to go ahead and sub in for the weight and put in mg. We all good? All right. That's the end of the force concept model. It generates two relationships, which you may or may not be able to use to solve your problem. Let's see if we can use it to solve our problem. I'm going to pull all the things together that I think we're going to need to solve the problem. Oh, I don't want that. I want this and that. I think these are the things that can be used to solve our problem. I'll remind you what we're looking for is T. And we want to put those things together so that we can get an answer. Things that can't be in our answer, well, this T for tension. That one can't be in our answer. V can't be in our answer. We are looking for the time, and we don't have the velocity, and we don't have the tension. We do have theta. We do have the mass. We know what G is. We know what L is. So we know what all of those things are, right? So we're trying to eliminate others. I think we should start by eliminating the tension. That's the easiest one to eliminate. We can do that right now by taking this and divide these two equations. You guys okay with that? I've done it a couple times with you guys. You're all good with us dividing this stuff on the left side and this stuff on the right side? Cancels out the t's and it cancels out the m's. So we'll get sine theta over cosine theta equals AC over G. Any question about that? All right, we could write that as tangent theta if we want. I'm going to hold off because I know in a little bit I'm going to be plugging in some other values for that are going to have sine theta in there. And who knows, maybe the sines will cancel or maybe something else will happen. I don't know. I think if I put tangent in there, I'm just going to end up splitting it back up to sine and cosine anyways. Is that all right? And maybe I'll be able to use tangent. I don't know. Let's take a look at some other substitutions we have to do. I don't know where you want to go first, but we got to get rid of this. I think a way to go first might be to combine these two things together. Is that okay with you guys? So I have AC equals V squared over R, but V equals 2 pi R over the period. So I think I can work period into the acceleration. That okay with you guys? You look confused. You don't like that idea. Do you want to do a different thing? Because we could do a different thing if you want. I just saw this and wanted to go this way. Okay. Well, nobody has an opinion, so that's what I'm going to do. That's 2 pi R over T squared over R. I'll remind you, you said you were good with us doing it symbolically, so we're doing it symbolically. Again, I'm still okay with it. I'm not scared of algebra. You guys tend to be, but I'm not. 2 pi times R squared is going to be 4 pi squared R squared divided by T squared divided by R. I just went ahead and distributed the square. Is that okay? I did that because I want to cancel one of the R's because I see an R there and an R there. I want to cancel one of the R's. And that leaves me with 4 pi squared R over T squared. That all good? All righty. I'm going to do my substitution then. Sine theta over cosine theta equals 4 pi squared R over T squared divided by G. I think we only have one thing left now, one more substitution to make, right? That's to get rid of the R and put it in terms of L and theta. So we're going to do this next. But before I do that, how about I simplify this and make this 4 pi squared R over G times T squared? That okay with you guys? Just simplifying my algebra a bit. Alrighty, so one more substitution, and we'll have sine theta over cosine theta equals 4 pi squared L sine theta all over GT squared. Messy, but not terrible. I do see that the sine theta cancels. Do you guys see that? I have a sine theta on both sides, so I can just Get rid of that sine theta. The cosine theta is not going anywhere, though. No, that's there. And we want to solve this for periods, so I think we're going to, I don't know, you guys have methods of doing this. I'm going to multiply both sides by period squared. That'll get it to one side. Is that okay with you guys? So I'll multiply period squared on this side and period squared on that side. And that cancels it out over here. So I'll rewrite this as period squared over cosine theta equals 4 pi squared L over G. All good? I'm just going one step at a time. I would probably skip a lot of these algebra steps, but I don't think that's good for you guys. But I'm just solving for periods, so I'm going to multiply both sides by cosine theta. Right? That gets period squared by itself. Real close now, right? All you have to do is take the square root of both sides. That okay with you guys? Yeah? No? Yeah, okay, good. So t equals the square root of 4 pi squared L cosine theta over G. So there, we did the whole thing symbolically. So we have one answer. We could do all sorts of stuff with this. I have a few of you who took AP Physics 1. And so you guys need to see something here. I think it's important that you see it. If we pull the 4 pi squared out, we get 2 pi times the root of L cosine theta over G. Now, if you paid any attention last year, this should look familiar to you, because anything that oscillated, any oscillation equation we had last year had 2 pi times the square root of something every time. And if you look closely at this one, this is the equation for a pendulum, except for that cosine. Right? This is the square root of L over G. And we had just 2 or 3 different oscillating properties last year. This is one. One of the things that is funny about this is that cosine actually is very close to 1 for small angles. And if you remember stuff about pendulums, you'll remember that we talked about small angles last year. There's a reason why that spinny thing and a pendulum have a lot in common, and why they rotate at about the same rate that they oscillate. So we'll talk about it later in the year when we cover vibrations and oscillations, but there's a reason this looks almost exactly the same. Now, with that being said, all you got to do is plug in your numbers, right? You'll notice the mass does not matter, but the length of the string matters, the angle mattered, and, of course, G is in this. So let's see what we get. T equals 2 pi times the root of, the length was 0.2. Remember where I put that in meters because G is in meters, times the cosine of 25 over 10. I'll let you work that out real quick, because then I want to talk about one more thing here. Hurry. Tell me it's 0.8 something seconds. So we got just under a second, 0.85 seconds or so. I'll let you all try, because everybody should try. You know, using your calculators and all, it's important work. So 0.85, but when you do this amount of algebra, which I know you think this looks like a lot, this isn't that much. It's just algebra. And algebra needs to be spot on. You got to be able to do algebra. There's simple rules, follow the rules. Sometimes it's not about the rules. Sometimes it's knowing what you should do next, what you should isolate, what you should substitute. You can substitute in any order. You just had to learn what things have to be eliminated and which things get to stay. That part's hard. That was the whole conversation here at the beginning is, what's my pathway going to be to get to my answer? That's why putting the numbers in makes that easier, because it takes away any thought process you have to have about what has to go and what has to stay. That's what makes the symbolic part harder. But we'll practice. I think that's the point of practicing. But when you make it to the end, it's hard to look at your answer, which is here, and have any idea whether it's right or not, right? Because you went through all that algebra. So how do you know if it's right? Well, one of the best ways to test something to see if it's right is to look at the units. Okay, just look at the units. The only thing that had units here was the L and the G. Nothing else has units there, right? Sine of an angle is a unitless answer. 2 pi is unitless here. So the only thing with units is L and G. L was a length. What's its unit? Meters. G is an acceleration. What's its unit? And this is all under the radical, right? Can you see that the meters cancels out and it leaves you with seconds squared under the radical? Because the second squared is in the denominator of the denominator. So multiply it, puts it up there in the numerator. So this is units of seconds. Are we expecting units of seconds for our answer? Yes. One of the ways to check any problem that has a symbolic answer is to check the units. On multiple choice, it's a great way to eliminate answers that are patently wrong. If you look at what they have for their distractors, any distractor that units don't work out for is not the answer. You can eliminate it immediately. So half the time, 2 of your multiple choice answers will work out to the wrong units. That'll help you eliminate them as possible answers right away. Since there's only 4 total, you can usually eliminate half by just looking at the units. All right. Like I said, I wanted to do 3 examples today. Ready for the next example? Everybody here listen to records, like the big things. Are any of you into records? Okay, so 3 of you. They are inferior to CDs, but nobody listens to CDs either. So, I'm okay with that. Having had my share of records, I can understand the infatuation with them. I miss buying a record from a record store. You should be able to tell me what setting a long play record would be set for, because you had to set the player. What are my choices for the settings of a record player? 78, close. Next. 16. There's 2 more. So you record people don't know, because you've not named either of the actual speeds that any of the records you would have access to are actually going to be set for. No. 45 and 33 1/3. Do you guys know what these are? That's right. These are the RPM settings that would be used for records. 78s were for old style Victrola players back in the 20s and 30s. They had to crank up. They spun really fast. Jukeboxes and singles were on 45s. Those are the small discs that had the big hole in the middle. The big hole was like that because those were played in jukeboxes, and jukebox armatures had to use the big hole to get the record to spin. The small hole was too small an error spot, so they couldn't spin the small record. Long plays had the little hole in the middle of the record, and they spun at 33 1/3 RPM. So if you bought a 45 generally had 1 song on each side. And so that's the way music was sent to radio stations in the old days. They were called disc jockeys because they were spinning discs in a booth, and that was what was sending music out across the airwaves. They haven't done that in years. It's all digital now. In fact, most of our local radio stations are all owned by big national conglomerates. There's very few independent stations anymore. But 33 1/3 was probably the records you guys have at your house. Or if you have them, you're just collecting them. They're probably long plays, 6, 5 songs on a side, and you flip it over. If you get into really some of the cool stuff, the label in the middle. Some people will hide songs underneath the label. So if you know certain artists who do that kind of stuff, Jack White is probably the only living artist, maybe Trent Reznor, who does some of that stuff with the records that they produce. So if you've ever heard of the under the label songs, there's secret songs underneath the labels of some records. You have to peel the label off and play it there. Just do a little research. Some people, they used to do really fun stuff with records that they just can't do today. Let's talk about 33 1/3. So you place the record on the player, it begins to spin. The whole thing has what's called an angular velocity. Right? That's the speed that the record is spinning. Every point on the record is spinning at 33 1/3 rotations per minute. In fact, there's a symbol we're going to use for angular speed later in the year. And that symbol is the Greek letter omega, but it's a lowercase omega. And I'm not going to go into it too much because we're not going to use it for this unit, but it's something to keep in mind. This Greek letter omega standing for angular speed. It's like a linear speed, but instead of how many meters per second you're covering, it's how many degrees per minute, or how many rotations per minute, or how many radians per minute, or second, or hour. Something is spinning. So the Earth has an angular speed of 1 rotation per day, right? So angular speeds, omega would stand for an angular speed. Do you realize that these 2 points on the record have the same angular speed? That they will take the same amount of time to go around once? Does that make sense? Are they traveling at the same linear speed? Which one's going faster, 1 or 2? 2, most certainly. Point 2 on the record is making a bigger circle in the same amount of time that it takes point 1 to make a circle on the record, correct? So this one goes around this circle in the same amount of time as this one goes around this circle. Agreed? So we understand what I mean by one of these has a bigger linear speed than the other. I don't know if you can do what I'm about to ask, but can you figure out how fast this point is going on the circle if I tell you that it is 10 centimeters away from the center? Do you have a method that you could use to figure this out? If not, I will give you a method. But do you have a method? None of you? How many of you think you could probably figure it out if given enough time? That's not very many of you. So I'm going to give you a method. It's not hard. We're going to use something called unit multipliers. And we're going to start by saying the record is spinning at 33 1/3 revolutions every minute. So take whatever your thing is and break it up into a fraction with 1 unit on top and 1 unit on the bottom. Okay? We're going to multiply by unit multipliers, meaning what goes in these parentheses are things that are going to convert from one unit to another. For example, I want to get rid of revolutions and be left with meters. Does that make sense? Right? I want to know how fast it's going in meters per second. I currently have revolutions per minute. So I'm going to convert revolutions to meters. Now this part's not particularly tough. You just need to know how long a revolution is. And I'd say a revolution is 1 circumference, correct? So 2 pi r meters for every 1 revolution. This is a unit multiplier that's going to convert from revolutions to meters. I'm just multiplying by a circumference. It's called a unit multiplier because we're not changing the value, we're just changing the units it's measured in. But I also don't want minutes either, so I'm going to use another unit multiplier to get rid of the minutes. But I'll notice minutes is on the bottom, so I want to cancel it out, so I'm going to put minutes here on the top and seconds on the bottom. So I need some way of converting from minutes to seconds. Do you guys have a method? Okay, good. Glad to hear that. So this is going to be a way to do it. This will convert you from revolutions per minute to meters per second. And can you work that out real quick and tell me that it's going to be like I don't know what it is. I think it's going to be 0.8 something, but I'll let you tell me. Maybe not 0.8 something. I don't remember. Be careful. That 10 has to be converted to 0.1, right? Meters. What do we get? Anyone far? But I want to tell you something. Where that little X is, what if there was a spider there? And the spider needs to hang on. My question, which I did get through in first period, is what coefficient of friction would be necessary for the spider to hang on? It takes about 2 minutes. You should probably watch those 2 minutes of first period's video. Okay?